about waveguide and cavity component design tools in, let's say, the CST Studio Suite environment. I will talk today about two main tools. I will talk more in deep about FES3D. And as in the first talk, we have been introducing WASNet. I will also give some comments on WASNet, which is a tool we recently acquired. Okay, so about FES3D, I will go through the main capabilities, analysis, optimization, synthesis, and RF breakdown. And I will also show the main link or links between FES3D and CST Studio Suite, how to communicate between both tools, and so on. Okay, so just a fast introduction. Well, we can say that for those components that FES3D can solve, it will solve them typically 1 order of magnitude faster than traditional full segmentation-based technique like finite elements or finite differences. Of course, the reason is that it is a dedicated software tool. You cannot solve everything. Okay, for the moment, we are handling here in FES3D waveguide and cavity components. And of course, thanks to the fact that it is a dedicated tool, we can use specific numerical techniques which are very efficient in those cases. Okay, so indeed, what we are using in FES3D is a modal approach. Okay. And that modal approach allows applying a divide and conquer method in which you can split the device in building blocks. Okay, I will go through this a little bit more in detail later on. Okay, so basically the modal technique we are using in FES3D is based on an integral equation solved with the method of moments. And of course, we are using the multi-mode network theory to connect all the different building blocks through the modes at the connection surfaces, let's say. As said, this is a divide and conquer strategy. So the main benefit is that you can use different methods depending on the particular part of the component you need to analyze. Okay, and you will see that more clear now that I will go through some of the methods that we use. So of course, in the case of canonical waveguides like rectangular, circular, or coaxial, the modal chart can be obtained analytically. Okay, and of course this is very efficient, right? However, there are many cases in which you want to use other type of, or you need to use other type of waveguides. And then specific methods can be applied to do this in a very efficient way. For instance, in our case, in FES3D, we are using the 2D Birman method, okay, to compute, let's say, arbitrarily shaped 2D waveguides. And the point here is that we are in the end computing the modes in the arbitrary waveguide as a function of the modes in a rectangular waveguide. This method is very efficient, especially when many frequency points are needed, like in a broadband analysis. So let's say that it is a method that combines the best of the two worlds in frequency domain and time domain. So you can still use frequency domain techniques, but you can apply it to a broadband case. We have extended that method not only for waveguides, but also to arbitrary shaped 2D cavities, so that they are constant in height and or width, so that basically the variations are in the propagation direction. So just for illustrate this better, you can see two examples here: a waffle iron filter, which would be solved with the 2D Birman method for waveguides, and a SIW filter, which would be solved with the 2D Birman method for 2D cavities. Okay, but of course, our life goes beyond 2D, and many times we also need to solve 3D building blocks inside a component or 3D parts. For the case in which we have metallic cavities, we have the extension from the 2D to the 3D Birman method. Okay, in which in this case, as before, but again in 3D, here what you are doing is computing the resonant modes in the cavity as a function of the modes, or in terms of the modes of the resonant rectangular cavity. In the end, this is an eigenvalue problem, and the benefit is that in the end you get a pole expansion of the generalized admittance matrix, and again this allows very fast frequency computations. These are two examples of filters or types of elements that components that you could analyze with this technique, okay, in which you really have 3D building blocks here. In order to extend this, because as I said, that this is working fine for metallic cavities, we have included a finite element solver into FAIR3D, okay? And the way we have done this has been by the integration of the high frequency domain solver of CST Studio Suite, okay? In this case, we use the fast reduced order model implementation, which allows, again, fast broadband calculations. And the connection with the rest of the circuit is done through a multimodal connection and ensuring, of course, accuracy, of course, if enough modes are taken into account. Thanks to this new implementation, we have extended the library of elements, so we have increased or improved the versatility of the tool. And now you can use FAIR3D to design the electric loaded cavity resonator filters or MTs. In general, it increases the versatility of the tool, as I said, allowing the simulation of more complex devices. So here you can see that we also have the possibility to analyze circular, coaxial T-junctions, rich bends, and so on. Okay, so just a few examples about FAIR3D. This is a very simple case in which, of course, FAIR3D is shining a lot, because we have everything in rectangular waveguide and we are connecting all the waveguides through the modal technique. And in this case, we are solving, I think in this case, 200 frequency points in just half a second, okay? Again, you can see the FAIR3D interface in which we are really building the structure, with building blocks, okay? You see here all the different blocks connecting and forming in the end the 3D model. A more complex case, it's this diplexing coaxial technology, okay? Again, you can see the complete structure built in CST in FAIR3D, okay, with the diplexer. In this case, we are talking about 75 seconds because we have several finite element elements there, parts there, like the bends or the coaxial T-junction. But of course, the filters would be solved pretty efficiently indeed. And this is important. I will come back to that when I'm talking about optimization. And this is also another example in which you can see the power of the tool. We are designing here a 10-channel or analyzing here a 10-channel output multiplexer. This is typical for space applications. And you see that you can solve the complete structure 3D full wave in just half a minute, okay? This could not be even possible to be solved with standard techniques based on segmentation like finite elements or finite differences, because you would blow up your computer. Okay, this was half a minute in a standard in a standard laptop. So you can see again here what is the benefit of using this type of technique. Okay, so as said, that was the part for analysis. We also have optimization capabilities, fully integrated optimizers like Powell, Simplex, or Gradient, which also incorporate the possibility to use arbitrary goal functions. And this is what I meant before that I wanted to remark now. There is an important aspect that boosts the performance of the optimization in FAIR3D, which is the fact that only those building blocks or those parts that are modified during optimization are recomputed. So the simulation time per iteration can be much lower than the computational time of the complete design of the complete component. Okay, in the case of the diplexer I showed before, if you have the T-junctions already calculated or the T-junction already calculated and the bends and so on, the simulation time is reduced a lot to a few seconds, okay? Finally, also, I think just I introduced before the link we have between CST and FAIR3D for the finite element solver, okay, in FAIR3D. We have another link, which is the possibility to run the FAIR3D solver inside the CST schematic, okay? And then This automatically brings many benefits of CST Studio Suite, like the CST optimizers that we have there, like the Trust Region Framework, and even also the use of the coupling matrix or through FD3D as a goal function for filter design. So this can even boost more the capabilities of having a fast solver. I will go into details about this later on in detail. Okay. So apart from optimization, we also have synthesis capabilities. So we are able to synthesize a number of different filters. For instance, wideband inductive bandpass filters like the one shown here, low-pass waveguide filters and transformers, and also dual mode filters with cylindrical cavities. Okay, so the idea here is that we have an automatic procedure or workflow to go from specs to the final design. The workflow looks like this. Okay. And this is just a typical workflow for all the tools, I would say. So of course, first the user has to provide the electrical specifications, such as the passband, out of band, and so on, and some basic information about dimensions of the component, like which ports you want to use, port size, and things like that. And then the synthesis tool will run based on that, but it will not run the complete structure. We are not analyzing here the complete structure, but we are designing the device step by step. So we will design the input-output irises, we will design then the cavities in this case, and then we can maybe design again for these dual mode filters the cross couplings and so on. And you never simulate the complete structure until the end. And then at the end, you can decide whether you need optimization or not. In many occasions, you don't need to post-optimize. That is especially true for the bandpass filters or the low-pass filters. For the dual mode filters, it's almost always fine because the main inaccuracies can come from the tuning screws, which are later on tuned during manufacturing. And indeed, for instance, in one case, in this case, this was the final design obtained. You can see the S parameter response without any kind of optimization. And of course, as I told you before, one nice thing is that once you are done in First3D with this optimization, with this synthesis, with this automatic design, you can automatically export this to CST Studio Suite, and everything will appear there. Okay, and indeed, everything is integrated, and you don't even need to do any action as a user. Everything will be open in the end in the CST Studio Suite schematic, and you can perform them there a further analysis to cross-check the results from First3D. Okay. So now going into detail for each case, okay, we have in the case of the inductive bandpass filter, several topologies are possible, such as rectangular iris couple, metal insets, and cylindrical pulse couplings. Also, inhomogeneous cavities can be used to improve the out-of-band response. And the nice point on this tool is that you can really achieve wide band responses like 10, 15, 20% of bandwidth. Of relative bandwidth without the need to post-optimize. Okay, this is just an example. Okay, of a 6-cavity filter with rounded corners, which was achieved without the need of post-optimization in less than 1 minute. Okay. And now I want to show you an application example of such a tool, okay, of this inductive filter. So for instance, in this case, we want to design a 10 kilowatt high power X-band diplexer for deep space communications. Here we have the bands for deep space communications. The return loss is 23 dB and isolation 130 dB. Okay, and then basically just before doing the complete design procedure, what we want to design in the end is something like that. Okay, we have the receiver and transmitter bands. Okay, and we want to combine them in one single channel. Okay, so how could we proceed to develop this diplexer? Well, the design procedure would start with these automatic synthesis tools in First3D so that you can design automatically the two filters, okay? And then you would combine those filters into a compensated T-junction. And here you will need to optimize the T-junction itself and the first, let's say, dimensions or the dimensions close, the filter dimensions close to the T. Okay, but you don't really need to optimize the complete filters again, just because the frequency separation is quite large. So you would only need to optimize a few parameters here. This will be very efficient. Later on, I will talk about the simulation time per iteration. And finally, you could add the bends. Okay, and again, you will need some refinement and optimization of the bends and the T-junction and some of the dimensions of the branch filters. The simulation time of this component is just 5 seconds for the complete frequency band. Okay, we are talking here about 200 or 300 frequency points. So each iteration would be as maximum just 5 seconds. Okay, as I explained before, if you are optimizing just one building block like the T-junction, then the simulation time would be lower. Okay, but just for you to understand a little bit what is the range of the simulation time we are talking about here. This duplexer indeed will be used in the next presentation by my colleague Michael to show the multiphysics workflow in CST Studio, the connection between the electromagnetic and thermal, or the coupling between the electromagnetic and thermal parts. So if you want to take a look to that, just stay in the room. Okay, for low-pass filters. In the case of low-pass filters, we also have several topologies, such as E-plane corrugated filters, coaxial filters, or rectangular capacitive iris filters. Again, typically, no post-optimization is needed. The only situation in which you need to post-optimize is when you want to add an impedance transformer. If you want to go from a standard waveguide to a reduced height filter, you need to use those transformers to do the adaptation. And then typically you will need to optimize a bit the structure. But again, this simulation will be quite fast indeed. Okay, so the last one, the circular waveguide dual mode filters. Okay, in this case, we are synthesizing from the coupling matrix. And we can do singly or doubly terminated filters. Singly terminated filters are mainly used for contiguous multiplexers, so this is really possible to be done. It's pretty flexible in terms of the resonant modes that can be considered, also the filter orders, and we can even do automatic group delay equalization for this type of filters. And now I want to show you an example of how to use this synthesis tool in a more, let's say, larger workflow. Okay, so the idea here is how to use this tool for multiplexer design. Okay, so here I show the workflow. Of course, you would start with the specifications. In this case, we are talking about a 6-channel multiplexer. The multiplexer is contiguous because the wide band is very small. So the channels are very close together in terms of frequency. Okay, for each channel filter, you can of course extract them a coupling matrix. This is FD3D as TNS was showing before. Okay, so we have a coupling matrix representation for the channels. At some point, you will need to decide which type of configuration of the multiplexer you want. And here we are selecting a manifold configuration in herringbone. Okay, so this is the type of multiplexer we want to design. And the first thing you would do is basically to connect the 3D and the circuit walls. Okay, this is one of the main advantages here. You would first, of course, build the structure, but you would not build a complete 3D model. What you are going to do, basically, is to build the manifold in 3D, also the stubs or the length from the filter to the manifold, but the filter representation will be the coupling matrix. Okay, you can say, or you can imagine that this simulation of this component here will be very fast because the coupling matrix is It's analytical, and the rest of elements are very efficiently solved. So the advantage here is that you can really optimize this very efficiently until you get the desired response here. Okay, and basically what you are doing is optimizing the manifold, the stubs, and the coupling matrix to obtain the response you want. Okay. So once you have that, and then you have your multiplexer design with the coupling matrix, what you need to do is to replace that coupling matrix by the actual 3D filter. And then you can do that, of course, with the synthesis tool I just introduced. Okay, so you would take that coupling matrix and automatically design the 3D filter. And then you would replace that filter, in this case is the first one, the one on the top here. You would replace the 3D filter, or you would replace that coupling matrix by the 3D filter, and then you can optimize again. Okay, you would optimize the filter and the manifold, the stubs, and the coupling matrix. Okay, and once you are fine again, you have to repeat this. Okay, and you need to repeat this for each channel. So in the end, you will be replacing the 6 coupling matrices by the 6 3D channel filters. But of course, the optimization procedure is much more efficient because you are adapting slowly the complete 3D model to the response you want. You are not just taking the complete 3D model and try to optimize that. That will not work. Okay, but with this step-by-step procedure, you can really get the multiplexer and your final design. Okay, changing of topic to RF breakdown, I will not talk much because I will indeed talk later on, but let's say that the Spark 3D, which is our dedicated tool for RF breakdown, is integrated into First 3D, so you can run it automatically from it and perform RF breakdown analysis, both multipacting and Corona. Okay, so just to finalize the first 3D part, you saw that I have introduced a couple of links. One is the possibility to use the finite element solver of CST inside First 3D, and that will allow us, or that allows us to simulate more complicated structures. And the second link I also mentioned briefly is that you have this First 3D block into the schematic of CST, okay, which allows us to use all the technology available in CST Studio Suite, like the optimizers, parametric analysis, and so on, and even combining this first 3D block with other blocks in the schematic, like an antenna, for instance. So I want to show you how this works. This is just a video going through the complete workflow and then even showing the simplification of the workflow, okay, that we have implemented. So first of all, you need to, of course, open the CST Studio Suite schematic, okay? And there in the block selection tree, you have the field simulators, and inside the field simulators, you have a First 3D block. So you can put it in the schematic, and automatically you have to select, or you will need to select a file, a First 3D project file. And this is loaded into the schematic. You can see it there. The project parameters, or the First 3D project parameters, are automatically set, and you can edit this. And edit this, what we'll do is to open that particular project of First 3D. Here we can see that we have the parameters that we imported, and we can also see that we have 2 accessible modes per port. So in the first port, we have 2 modes. In the second port, we also have 2 modes. Okay. So then we can close this and come back to the schematic. And these 2 modes is what you see there because you have 2 pins per 2 ports, so 4 pins. So now we need to connect the external ports to the first mode of port 1 and to the first mode of port 2. And the other higher modes are just connected to absorbers, okay, to ensure that energy is properly preserved and that the simulation will be okay. So once you do that, then what you have to do is to come back to the tree, to the navigation tree, and add a S parameter task. You add it. This S parameter task will have automatically the frequency range in the First 3D project, and you can just update it. The update will basically run the block with the First 3D solver. Okay, so this simulation will be very fast because it's just using First 3D. And here we can see the simulation results. So now, how can we improve this? So how can we improve this workflow to automatize it so that you don't need to go through everything? So, okay, now imagine we are in First 3D with the same project. And I will show you several parts. So the frequency sweeps, we have a couple of frequency sweeps here. Okay. We also have the optimization setup where we have the parameters. And we also have the goal function for the optimization below. Okay. Apart from that, we also have defined a field monitor, okay, at 11.2 gigahertz. And then we are going to export this directly to the circuit. Okay, so there's a button, you export it. You have two options added to create automatically the 3D simulation project and the optimization task. We say yes, we keep the name, and then automatically this will be exported to CST. This is done automatically, you don't need to do anything else. So first of all, you can see that we have already global parameters automatically created, so ready to be optimized if needed. You see that the ports are automatically created and connected to the fundamental mode in each port. And you can also see that absorbers are automatically connected to the higher modes. Okay, so everything is set up. Now, if we go to the tree, you see that the S parameter tasks are automatically set. Okay, the S parameters are taking the frequency ranges we have defined already. In First 3D, the simulation project has been created again automatically. Okay, and there is also an automatically created optimization task where you have the parameters to be optimized, and even the goal function from First 3D is automatically set. Okay, we can also check that we have the simulation project. So you could run automatically this project in CST with the frequency domain. And even we also have the field monitors we define in First 3D. Okay, so everything is automatically exported. Okay, so once I have shown this to you, I move to WASNet very briefly. Okay, I think this slide has been indeed introduced by my colleague in the first talk of the day. So this is a recently acquired tool, okay, at the beginning of 2023, with a very specialized solution for waveguide and antenna structures, okay? So the idea here is, like in the case of First 3D, is to highly efficiently solve components in very short times. So it uses different methods. It is based on mode matching, but again, it's also using hybrid methods like finite elements, method of moments, iterative physical optics, or physical theory of diffraction. And you can really optimize the complete field network together with antennas. Very interestingly, it has very nice design wizards for antennas, especially, okay, where you can really design reflectors or slot arrays, okay, or horn antennas. And it has a very large designer database. So you have models that are completely parameterized and that you can then change and use them by yourself to the specific frequency range you are working on. And of course, the idea basically is that this will complement and extend the CST Studio Suite technology. Just very briefly, here is an example of one of the wizards, the slot array waveguide antenna wizard. Here we are talking about more than 180 slots. Okay, and this can be really designed automatically in just around 20 minutes, including all the optimization or ad hoc optimization that you have in there for this type of arrays. Okay, and just finally, we have another example of this horn antenna where the 3D model is built automatically. Okay, and again, the simulation time per frequency point in this case is just 2 seconds, which is very, very efficient thanks to the symmetries used. And then this really helps you to design this type of components and antennas very efficiently. So summary, key takeaways. So First 3D is a very specific tool for waveguide and cavity-based components. It has specific capabilities for filter design. And interestingly, it has two-way integration with CST Studio Suite. And I have also very briefly introduced WASNet, so that it is a tool we recently acquired, which is very nice and has very nice specific technology for antenna analysis and design specifically. Thank you for your attention.